Okay, so I think as we were talking about power last time, you're working out of Chapter 10 of your textbook. We wanted to tackle this problem where we were given the voltage that was in time domain, which of course we could say that if it were to put it into phasor domain would be equal to 40 at an angle of 30, right? We're given the impedance and we'd like to find the instantaneous power and the average power. That's either supplied by the source or absorbed by the impedance. Either one will be the same because there's one source and one impedance. Well, we know that, of course, with Ohm's law, that voltage is equal to current times the impedance Z. So we could say then that the current I is equal to the voltage V, the phasor voltage, divided by the impedance. So let's make that work out. We'd have then 40 at 30 divided by the impedance 20 at 60, which gives me then 2 would be dividing the magnitudes, and then I have an angle of 30 minus 60, so I end up with minus 30. So that's going to be amps. Okay. That one you can do in your head pretty easily. A lot of people in lab yesterday still haven't mastered their calculator, so find someone their calculator that looks like yours, ask them how to make it work, spend some time on Google with your owner's manual, but you want to be able to do these numbers on your calculator. So we've got the current. I could put this into the time domain if I wanted to then. I could say that I in the time domain would be equal to 2 times the cosine of, where's our omega? I guess we don't have omega. They just told us omega, so we'll just repeat that, omega, t, and then we've got what, minus 30? So that would be the current. So if I look at the instantaneous power, looking first at the instantaneous power, this is probably the only example we use on instantaneous power. Probably one of its greatest uses was the calculation of average power, which we will do quite a bit. But let's look at the instantaneous power. We could say that the instantaneous power, that's going to be equal to 1/2 times the magnitude of the current, which is 2, times the magnitude of the voltage, which is 40, times then, we're going back to the equation that we'd finished up with last time, we're going to have the cosine of the difference between the phase angles of the voltage and the current, so I will have 30 minus a minus 30. It's the difference between the phase angles of the voltage and the current, plus, and then I had this term, the cosine of 2 times omega. I don't know what omega is, so I'll just write it as omega t plus 30 plus a minus 30. Remember we had those terms. This one was, this term here was not a function of time, whereas this one was a function of time. So when you go through that and clean it up a little bit, we end up with 40 times the cosine of 60, a minus and a minus is a positive, cosine of 60, plus the cosine of 2. See, 30 minus 30, that'll cancel each other out, so I just have omega t, right? And this would be watts. That's about as far as we can go for the instantaneous power, unless someone tells us what omega is and what time. Okay, it's instantaneous, so we would need to know what time they are talking about. But that's the expression there. Like I said, that's probably the only example I'll ever do with instantaneous power. We do a lot more with average power. So let's look at average. So if we talk about average or maybe real power, goes by both names. We had an expression where wasn't that average power was equal to 1/2 times the magnitude of the voltage times the magnitude of the current times the cosine of theta minus phi. You remember that? Okay. So I could talk about the average power being equal to 1/2. What's the magnitude of my voltage? 40 times the magnitude of the current. That's going to be 2. Times the cosine of the angle of the voltage, which is 30, minus the angle of the current, which is a minus 30, so which turns out to be what? 40 times the cosine of 60, which nets me 20 watts. You notice I don't need time for that. It's the average over one period, so it doesn't matter what time it is. So we weren't given time in this, and I actually couldn't finish up the instantaneous power, but it didn't matter for the average power. The thing we learned last time was what dissipates average power or real power? Resistors, and resistors only, right? The average power for inductors and capacitors is equal to 0. Questions with that? Well, we're going to continue on in power, talk about RMS and effective values and things like that. But there seemed to be some angst in lab about what's leading and lagging. So I wanted to talk a little bit about this. I guess I don't have my backing sheet here. There we go. So let's say that I look at this in a phasor diagram. So I'm going to go on to the imaginary, and remember I misspelled imaginary, or the abbreviation for imaginary. It should be what, IMG, that would be an abbreviation. Yes, question?
For all these functions, are frequencies are always angular velocity is always the same? 377.
Omega? Angular frequency? Well, we'll see it as angular velocity in dynamics, yeah, but in here we'd like to call it angular frequency. Or, I mean, the frequency, radians per second. Okay?
What I'm saying is, can you only do all of this when those frequencies are the same?
They have to be the same, yeah. I mean, if I'm working a problem and we're talking about the current and the voltage, we would expect these numbers to be the same. Okay? Yeah. You go to another problem, they could be different.
Is there a say, can you not have different frequencies?
Well, within the problem, they'd have to be the same. But for instance, I mean, if we're running, for instance, in this room right here at 60 cycles, we're running 377. You go to parts of Japan or something, they're going to run 50 cycles, so they're running some other number a little less than 377. But if you're looking at voltage and current, they would have to be the same. Okay? Which is also another point. People got hung up in lab yesterday. They kept wanting to use 377. Well, we were using 10,000 or 30,000 hertz, which means we were a lot different than 377. But if we have one value that's at 377, all of the others are going to have to be there. Now we might talk spring term about putting different frequencies down a line at the same time, but for our purposes now, if your voltage is one frequency, the current would have to be the same. Other questions? So let's say that I take, I've got the imaginary plane here, so this is the J direction. I got the real here, and I put a voltage phasor at 60 degrees. I've got a current at minus 30. So if I write those in phasor form, I just picked a magnitude. Voltage is 100 at 60. Current is 150 at minus 30. And if I wanted to, I could put them into time domain. And I think it's a lot easier to recognize which one's leading and lagging if you look at it in phasor domain. We would say that the voltage would be leading, right? And the current would be lagging. But if you want to prove that to yourself, you could put these into time domain. So write them out in the time domain with a cosine function and plot them. You plot them on your calculator with a computer algebra system, and you get something like this. And if I take one of them where it crosses at 0 and I look at the other one, if this is the voltage function here, and this is the current function, what do we have leading and lagging? You got the voltage leading, don't you? And this would be our phase shift in here. Yes, question back there. Not necessarily, no. I mean, when you look at the oscilloscope, you can't tell which is voltage or current. In fact, neither one is current, because the oscilloscope is measuring voltage. It's we take one of the voltages and we divide by resistance, and that's where we get the current. Okay, so those that have been struggling talking about leading and lagging, if this makes more sense going into the time domain, and I think it's more difficult to see in the time domain, but if this helps people in the time domain, that's what you've got going on. Now, probably in lab, I'll convince you, or maybe not convince you. But instead of having these two odd angles here, I say, well, why don't you put one of them here so that you could say, for instance, I like to put I as equal to some magnitude at some zero phase shift. And then we have the voltage either here or we have the voltage there, right? If this is the voltage, we're going to be thinking that V is leading I. So that's what? Eli? So this would be for an inductor. If our voltage is down here, what do we have? Ice, the current leading the voltage. So this would be for a cap. Okay. And then this angle that is taking place in here, whether it's you're looking at this angle here or you're looking at that angle in there, that ties into your phasor diagram, right? Up here with the inductor, you're going to have a phasor diagram that looks something like this with the resistance of the inductor and then J omega L. This angle here is that angle there. Whereas with the capacitor, what's your phasor diagram look like? Looks like that, where you have some probably very small value of resistance, minus 1 over, or minus J over omega C here. And this angle is going to be that angle, isn't it? Okay. So just a few things that I wanted to point out. Hopefully that helps the group tomorrow. If you were the group in lab yesterday, hopefully this will maybe put a few issues to rest. Probably the biggest thing is just doing homework problems, writing up lab number 1 and doing homework problems. This is like riding a bicycle, right? You can watch all the videos you want about it. You can look at all the pictures you want about it, but until you grab hold, pull yourself up onto it and try and make it happen, it's just not the same. So start writing up that first lab, start doing the homework questions. You're going to come up with some good questions, and in the process, hopefully learn something. Questions of that? Okay, so that was a bit of an aside there, but I think important. Let's move back to power. And one of the things with power is keeping track of all the names. The next thing we're going to go on and we're going to talk about is RMS, or effective value. I don't know if you noticed, but when we had the average power expression, we said that power average is equal to 1/2 times Vm times Im times the cosine of theta minus phi. And for a resistor, this was equal to 0 for a resistor, wasn't it? So we came up with this expression there. We put a box around that. People remember that and use that. But I don't know if you had a concern. I mean, why in the world do we have 1/2 there? We had resistors last term, we didn't have a 1/2. So why when we go from AC, or why when we go from DC last term to AC this term, do we all of a sudden pick up a 1/2? Well, the answer to that is in what we call the effective value, or the RMS value. And I'll probably use RMS from now on. Those two terms are somewhat interchangeable. But I'll probably talk about the RMS. So if we talk about the RMS, which if I were to try and define that very quickly, it's really the DC equivalent of an AC. So if you were to take this sinusoid, like this, and you were to try and get the same amount of power that you could get from that sinusoid out of a DC source, how much DC source would you have? That's what RMS is. Okay? And in fact, when we look at the plug-in like it's on the wall here, and we talk about 110 or 120, that's actually RMS. So the peak value, if you choose to get shocked at this time here, is actually larger than 110 or 120. We'll give you the numbers on that in a moment. So if we talk about RMS values, we could say that the average power, or the real power, remember we use average and real interchangeably, is equal to VRMS times IRMS. So I can get rid of that 1/2. Or I could say, our old friend, there's IRMS squared times R, or I could talk about that it's equal to VRMS squared over R. So instead of using maximum values, instead of using peak values, I use RMS values. I can get rid of that 1/2. Okay? So how do you calculate RMS? Well, RMS is an acronym. It stands for root mean squared. Root mean squared. And you have to do it in that order. You have, well, I guess the reverse order that you read it, you have to square the term. You have to take the mean or the average. Those two terms are interchangeable, and then you take the square root. Sometimes students like to change the order, and they like to say, well, I'm going to square it, and then I'm going to take the square root, and then I'm going to take the average. I get back to where I start, right? Okay, you can't do that. You have to square it. So I'm going to take my function, and you'll notice that I put this in terms of x. I could say x RMS or x effective. If we're talking about effective, it would be the same thing. I haven't committed to current or voltage. We introduced this in this class, so usually we're talking about in terms of current or voltage, so you substitute that x for a V for voltage or I for current. But we could talk about an RMS value for anything that's periodic. We could talk about an RMS value for temperature. Heats up during the day, cools down at night. Is there an RMS value? Yeah. Okay. So it's not something that is strictly related to electrical, although it fits very nicely into electrical, so we talk about it now. So whether this is voltage or current or something else, what we do is we take the function, we square it, so it's a function of time, we square it, we add it up over a period, and we divide by the period. That's taking the average, and then we take the square root of it. So we square it, we find the average, and then we take the square root. So that's the RMS calculation, and we'll come back and get some practice using that. If you read through Chapter 9, your author did this in a little different order than I'm doing. I'm actually in Chapter 10 now, but your author talked about RMS in Chapter 9, kind of spoiled the surprise, but that's okay. If we look at a sine or cosine wave, so for a sine or cosine for that matter, we can say then that V RMS is equal to the maximum value divided by the square root of 2. Okay? I guess we should not leave current out. We could say that the magnitude, and you'll notice I'm not writing these with the phasor dot because they're just the magnitudes. The magnitude RMS for the current would be equal to the maximum value of the current, the peak value of the current, divided by the square root of 2. Now I could rearrange these if I wanted to and say that root 2 times V RMS is equal to V max, and if you will, that root 2 times I RMS is equal to I max. Okay? So if you go through this calculation up here, we're going to go through it for some different functions. We're not going to do a sine wave, but if you did it for a sine wave, you'd come up with a factor of the square root of 2. So if I go back to this equation here then, so I'll substitute these in. Substituting those in, I can say that my average power is equal to 1/2 times V max times I max, the magnitudes of those, which is 1/2. Now let me make my substitution. What's another name for V max? I have the square root of 2 times V RMS. And what do I have then for I magnitude? Square root of 2 times I RMS. What's root 2 times root 2? Gives me 2, cancels with 1/2. Doesn't this turn out to be equal to then V RMS times I RMS? Yeah. Okay. So the answer to why you had 1/2 was it was just the unit or the measurement that we were using. If you go back and you use an RMS value, this looks exactly like what we had last term. Okay. So to some extent, this makes things easier. To some extent, it makes it more difficult. We have yet more equations. I mean, you have 2 valid equations. Pull this up here. Okay, good. There we go. I guess I'm messing up my. This is so. This is page 3.1. There we go. We'll be real fancy. So we have very valid equations that the average power is equal to 1/2 V max times I max, or we could say that the average power is equal to what? V RMS times I RMS. Okay. Well, let's see. This actually works for all. What does this work for? Actually, just a sine or a cosine. So if we start looking at square waves, triangular waves, and whatnot, we probably should use that. Okay. And eventually, we will probably use this quite a bit more than we'll use that. Well, let's go back and look at how to calculate. How can I calculate an RMS value? So we'll just go through this. Here's a triangular wave, and we'll see if we can calculate an RMS value for this. So I'm going to look at 1 period on this thing. Usually I start here at 0 and go for 1 period. So you could start anywhere you wanted to. I think this probably keeps life easier if you start at 0. So I'm going to say that if I wanted the RMS value, I could say that I RMS, that's going to be equal to what? The square root of 1 over the period times the integral from t naught, which is 0, to t naught plus a period of I squared t dt, right? Okay. So let's see, if I'm squaring it, could I say that the integral from t naught to t naught plus t of I squared t dt, would that be the same as saying it's 4 times the integral from 0 to t over 4 of I squared t dt? Is that fair? I mean, I'm really just then looking at this piece, right? That should work, shouldn't it? And the reason for doing that is I don't want to have to do all 4 of these segments. So this should be a nice shortcut. If you don't like it, you could parameterize each one of those and break up the integral into, what, 3 pieces. But I'll use this as a shortcut. So I'm going to then find 4 times the integral from 0 to t over 4 of I. For this period, what is I? Well, it has a rise of the peak value divided by the run of t over 4. I have to multiply that by t and add 0 to that. That's the y-intercept, isn't it? So we could say then that this was equal to what? 4 times the peak value divided by the period times t. I'm going to have to square that, dt. So if I keep working my math here, what am I going to come up with? 4 times the integral from 0 to t over 4 of, I'll have 16, whatever my peak value is, squared, divided by the period squared, times t squared dt. So let's see, we've got then 4 times 16 as a constant. The peak value is a constant. T squared is a constant. So I really just have the integral from 0 to t over 4 of t squared dt. I think we can handle that. So we've got 64 peak value squared divided by t squared times t cubed divided by 3, evaluated at 0 and t over 4. So what are we going to have here? t cubed divided by 4 cubed minus 0. (64) peak value squared times t divided by 4 cubed. Let's see, what's 4 cubed? That's 64, isn't it? So this turns out to be equal to, I think I left a 3 off somewhere, didn't I? Yeah, let's see, where did I lose my 3 at? Evaluated there. Yeah, this would have to be 3 times 4, wouldn't it? So I'd have a 3 here. And I get to cancel that with that. Yeah. So I've got the peak value squared times the period divided by 3. Okay, that works. Now, what part have we found? We've really just found this part here. So we found this piece of this, haven't we? Okay. So I'm going to substitute that in rather than having to write the radical and whatnot each time. I'll substitute that in, so I can now say that I RMS is equal to the square root 1 over t. I mean, if you had numbers, you could plug them in. We'll do some problems with numbers. We're just doing this in the variable form. And then I have this whole thing that we have there, the peak value squared times t divided by 3. So what's that turn out to be? I get to cancel that with that. And we get the peak value divided by the square root of 3. So we can say with this that the RMS value is equal to the peak value divided by the square root of 3. So instead of square root of 2 like you have for a sinusoidal signal, we have the square root of 3. One thing that you always know is it's going to be something less than the peak value. Does it seem reasonable that the RMS value would be up here greater than the peak value? That doesn't really make sense, does it? So we know that our answer is going to be somewhere between this peak value and that peak value. So if we put that in there, it's right there, and indeed the DC equivalent. So you can do a few things math-wise to make your life a little bit easier as you go through this. Questions with that? Yes?
So,
yeah, because I wanted to split this up, and so I just figured the answer for that piece and multiplied it by 4. So I didn't have to break the integral up. Other questions? So whenever you get a question like this on a test, some students, let's say that your peak value was 1, we'd expect our answer to be between plus and minus 1, wouldn't we? In fact, it was always going to be between 0 and 1 in this particular problem. So if you get an answer of 3, do you think you're right? No. Okay. So check and make sure it makes sense. Well, speaking of stepping back and asking if something makes sense, let's try this next one. So let's say I have a square wave like this. So I have a square wave that goes, we've got it shown here at a minus x max up to a positive x max value. And it just keeps dropping between x max positive and x max negative. And I'm going to look at one period from there to there. Okay. Now, if you're one of those that kind of thinks outside the box, you may already recognize the answer to this. But we'll go through it. So if I do the same thing that I did before, I mean, we could say that x RMS is equal to the square root of 1 over t times the integral from, we'll say, 0 to t of, this is going to be x max, or whatever our function is, x of t squared dt, right? And if I have to square it, it's the same top or bottom, isn't it? If I have a negative number, I square it, I get the same number if I get a positive number and square it. So what I'm going to do is I'm going to save a little time here, and I'm going to say that 2 times the integral from 0 to t over 2 of x max squared dt is the same thing as the integral from 0 to t of x of t squared dt. This one is probably a little easier to see than the last one, but that should be fair game there. So when I do this, I'll have 2 times x max squared times the integral from 0 to t over 2 of dt, which is going to give me 2x max squared times t evaluated at 0 and t over 2, which gives me 2x max squared times t divided by 2, or I will have x max squared times t, right? Now that's just, again, this piece here. So let me say then x RMS, that's going to be equal to the square root of 1 over t times what we had there, x max squared times t. Well, I get to cancel that with that, and the square root of x max squared is x max. So we can say that x RMS is equal to x max. Does that make sense? Like I said, some people that maybe have seen this before in math or whatnot can step back from this and say, well, yeah, if I have a DC equivalent, it's got to be the same as that, doesn't it? Interestingly enough, if you get into welding technology and whatnot in the last about 20 to 30 years, instead of using an AC signal, we've started with a solid state and whatnot, starting to use more square wave signals because we can get more power. We can put more power into the material with a square wave signal. So they'll look at people that use square wave power sources because they don't have any square root of 2 in here, right? Well, I think the last one that I want to talk about today, and we may not get through this, but this will be the first one that we do with numbers, so this is kind of good. I'd like to find the RMS value. We could do voltage, we could do current, we could do temperature. It seems like we've done a lot of current, but that's fine. We could do voltage. I've got the time here, and I need to figure out where one period for this wave is. It looks like it comes up and it has a discontinuity and then comes up again and then is at 0. So I'm going to submit that this is one period. So the period is going to go from 0 to 3 and then starts over again. I think you hopefully will recognize that. So to do this, I don't have, I mean, I can't take this one here and multiply it by 3 because that's not going to work from 2 to 3, is it? So this is probably a good example of one that I really have to grind through. I've got to look at this for t from 0 to 1, and then I've got to look at it for t from 1 to 2, and then I've got to look at it for t from 2 to 3. And as you start looking at this, you'll recognize if you're doing group study, you would want this one here. Okay. Let's fill out these other ones. What's this one? It's going to have a rise of 2 divided by a run of 1. So I could say that this was 2 over 1 times t, plus, of course, 0 for the y-intercept. What's this one going to be here? I could say that also has a rise of 2 over a run of 1. Is that right? But if I put 1 in for that, I get 2, don't I? And I really want minus 2. So the y-intercept should be what? Minus 4? Does that work now? What if I put 2 in? Do I get 0? Yeah. So I will have 2 over 1 times t minus 4. Okay. So you can see why I tried to do the shortcuts on the other ones. I mean, this is going to take some work, isn't it? I mean, before I'm done, I'm going to have I RMS is equal to the square root of a great big mess. What are we going to have? The period is 3, so 1 over the period times the integral. I'm not going to break my integral up. I'm going to go from 0 to 1, and what am I doing there? 2t squared dt plus the integral from 1 to 2 of 2t minus 4 squared dt. Be real careful about that. You got to FOIL that thing out. Plus, if you forget about this one, you're probably okay, because this should turn out to be 0, shouldn't it? You're going to go from 2 to 3 of 0 squared dt. You know, I said, well, does this affect it? Yeah, it actually does, because it changed what? Changed the period, didn't it? Okay. So that's what we're going to have to go through on those other ones. If I didn't do that little shortcut, we would have had to have done something like this, and you can test those out. This is probably a pretty good stopping point. I will leave it at this point. You can run the numbers on it and see if you get the same answer that I do on next time we get together. I give you a hint here. Your answer's got to be between what? 0 and 2. So if you get 17, you made a mistake somewhere, right? Okay. We'll pick up and continue on there next time. Take care.